Hi, this is Justin Mansell from Active Optical Systems, doing an experiment here in the AOS software with one of the Holochip liquid lenses. So I've set up the liquid lens to be on channel 13 of this deformable mirror architecture, and I've already configured the network DM drive electronics, and so I can click here and change the focus of this liquid lens. I've already made some adjustments to the camera settings, so I get approximately 85% of the maximum range on this camera. And the camera I'm using, or the Wavefront sensor I'm using, is built off of a Marlin camera. So I'm seeing a noise floor right now of about 14 nanometers. Let me create a new reference and continuous acquire for a little bit here. We're seeing so something like 6 nanometer kind of noise in the system. What I can do is put this into continuous acquire mode, and it's finding a little bit of focus term there, and I can change the voltage on the liquid lens. You can see I'm getting your classic focus pattern there, and I can increment that up. You can see I'm getting a lot of focus term, a little bit of tilt term showing up here. It could just be misalignment, and not much else happening in the higher order Zernikeys. In fact, let's go in here, and that's set up at 12 already, but we can make it 20 higher order Zernikeys. I think that's pretty reasonable here. And so go continuous acquire again and bring this up. I think I'm now, yes, very clearly in this image and here, exceeding the dynamic range of the sensor. So let me bring it back a little bit. There we go. That looks pretty good at about 148 volts. Because of the magnification in getting the liquid lens onto the Wavefront sensor, I've had to I amplify a lot of these slope terms, and so I am very quickly exceeding the dynamic range of the sensor with the liquid lens. But I'm pretty close to it here. Let me go into zoom image mode and take a look accurately at these edges. Yeah, we're pushing right up against it at 148 volts. Now, we can go in and make some adjustments and try to alleviate that, but for now I'm going to leave that alone and see if we can collect some data here. Specifically, what I'm interested in is, at 148 volts, how much other aberrations are existing. Just to make sure I am not hitting that dynamic range issue, I'm going to bring it back even a little bit more. We'll call it 118 volts. This looks like the spots are in the boxes. That looks pretty good. What I want to do in the analysis window here is go in and subtract off the low order terms. So this is 1 to 2. I'll have subtract the fit there, and 4, which I know I'm varying. I'll subtract the Zernike fit there, and we can take a look at what's left. Aha! So the big standout in the reconstruction and even in the Zernike decomposition is the 12th one, which is spherical aberration, and this is expected of any of these kind of lenses. But you can see that I'm getting about 100 at 118 volts. I'm seeing about 100 and probably, let's see, that's 25, maybe 30-ish, I guess, nanometers of spherical aberration. But this gives you the decomposition at that high voltage. I'm going to save this data out. I'll just put it on my desktop for now and call it Holochip 118 volts differential. And this analysis window, I'm going to go back to this analysis window here, make sure that I can start logging some of this data. Let me do a single acquire there, and that's 118 volts. Let's bring it back down to 88 volts. A little bit of spherical still there. There's 59 volts. 30 volts. And we're back to almost perfectly flat. So this is a quick demo of how the AOS software can be used to measure one of the Holochip liquid lenses.